So in today's lecture, we are going to discuss about modeling of electrical systems. So the electrical system modeling can be obtained using the three basic elements of electrical system. They are the resistor, inductor, and the capacitor. So using these three components, we can obtain the model of any electrical systems. The current voltage relation of resistor, inductor, and capacitor. So if it is possible to write the current voltage relationship of these resistor, inductor, and capacitor, so it is easy to model any electrical system using these three basic elements. So let us see how we are modeling these three basic elements. So circuit model of a resistor. So here in this diagram, in this slide, you can see the circuit model of a resistor. So here, a resistor which is connected across the voltage source V of t, and by using the simple Ohm's law, we can write the voltage current relationship. So here the voltage V of t is equal to I of t into R. So this is nothing but your Ohm's law. So already you are familiar with this. And or we can write the current I of t is equal to V of t divided by R. Similarly, the another component. The inductor, you can see here, this is the circuit model of an inductor. Here also we can write the input output relationship using this Faraday's law, that is V of t is equal to L into d by dt of I of t, the derivative of the current, or we can write the I of t is equal to the current equal to 1 by L into integral V into dt. So this is the circuit model of an inductor. Similarly, we are having the circuit model of the capacitor here. So it is nothing but the voltage across this capacitor is V of t is equal to 1 by C into integral I of t. So you are much familiar with all these things because you have learned the circuit, all these things in your signals and systems or in electronic circuits one, and you can easily write the voltage across the capacitor, or voltage across the inductor, or voltage across the resistor. So if you know the voltage current relationship between across these three basic elements, we can model any circuit. So let us see an example. So here you are having an RLC circuit. So the question is, we need to write the differential equations that representing the electrical system. So here the voltage is V of t, the applied voltage is V of t, and the resistance R, L, and C are connected in series, and the current flowing through the circuit is assumed to be I of t, right? So the total voltage or applied voltage V, which is equal to, or V, or we can write, since it is a sinusoidal signal, we can write it as V or V of t, right? So this V of t is equal to the sum of the drop across these three elements, that is the voltage across the first element, the resistance, that is VR, plus the voltage across the inductor, that we can write it as VL, plus this voltage across this capacitance VC, right? Or we can write V of t is equal to, we can write V of t is equal to the voltage across the resistor is R into I of t, isn't it? R into I of t, a time varying current. R into I of t plus VL is nothing but L into differential of I of t, di of t divided by dt, isn't it? Plus the voltage across the capacitor is, of course, 1 by C into integral I of t into dt, integral I of t into dt. So this is what the mathematical equation that represents this circuit, right? Similarly, you can apply the KVL or KCL, Kirchhoff's current law or Kirchhoff's voltage law, to find the mathematical equations of any such a circuit. You see another one example. So here we need to find the transfer function of this system. this circuit. Okay, so to find the transfer function of the, so this is the question what is given, right? So how to find? So here the input applied voltage is VI, and the capacitor is C, right? The capacitance is C, and the voltage output voltage is represented as V naught, and the resistance is R. So we need to find the transfer function of the network. Transfer function means the ratio of the Laplace transform of the output to the Laplace transform of the input. So here you can write the input output relationship using the voltage equation. So here you can assume a current I of t. You can assume a current I of t in this circuit, right? So this is the current what you assumed. So now we can write Vi of t is equal to the input voltage. Vi of t is equal to. So if you apply the KVL to this loop, through this loop, right? So we can write 1 by C into integral I of t into dt, integral I of t into dt plus R into I of t, plus R into I of t, right? So this is what the input equation. Then output equation, the output is taken across this resistor, right? Therefore, we can write V naught of t is equal to what? R into I of t, R into I of t. That much. So now to find the transfer function is nothing but the Laplace transform of the output to the Laplace transform of the input. Therefore, to find the transfer function, you just apply Laplace transform to these two equations. Okay, so you apply Laplace transform so that we can write what is the Laplace transform of Vi of t. It is simply Vi of s. Okay, Vi of s. Right? So Vi of s is equal to 1 by Cs into 1 by C into S into I of s, okay, plus R into I of s. I of t, the Laplace transform of I of t is I of s. Therefore, R into capital letter I of s. So this is your first equation, right? Now you can write apply the Laplace transform to this equation, the output equation, that is V naught of s. V naught of s is equal to V naught of S, which is equal to R into I of S, R into capital I of S. Now you see, so this is your second equation. Therefore, this transfer function, the transfer function is equal to the ratio V naught of S, the ratio V naught of S divided by Vi of S. Okay, so this is what the transfer function. So we can write this as which is equal to, so what is V naught of S? R into I of S. This is your V naught of S, R into I of S divided by 1 by Cs, 1 by Cs into I of S plus R into I of S. So you can R into I of S. So you can take this I of S, factor I of S is common. Therefore, we can write this as which is equal to R into R divided by 1 by Cs plus R. Okay. So if you want, you can simplify it. This is what the simple transfer function of this network, the given network. Understood or not? You see the next one. Okay. Next, we are going to see these analogous systems. Okay, the electrical analogues of mechanical translational systems. So already we have discussed about these mechanical translational systems. Now we are going to draw its equivalent. Analogous means equivalent electrical system. Similarly, we can convert an electrical system into its mechanical counterpart, as well as mechanical system into electrical system also. So in the analogous system, so they have the same type of equations, even though they have different physical appearances, right? So electrical system, they has two types of inputs, right? As you all know, the electrical system has two types of input. It can be either a current source or a voltage source, right? It can be either a current source or it can be a voltage source. So based on these two type of inputs, so we can we can classify the analogous system into two categories, that is force voltage analogy and force current analogy. So there are two analogous systems corresponding to a mechanical translational system. So we have discussed some of the basics about these mechanical translational systems, right? So here we can draw its equivalent force voltage analogy as well as force current analogy. So see here how to change the elements from the mechanical elements of mechanical system to its equivalent force current as well as force voltage analogy. You see, so in mechanical system, the force F, it is represented in force voltage analogy. The force is represented as voltage. Understood? The corresponding the voltage corresponds to, or the equivalent quantity, which corresponds to force, is voltage in the case of force voltage analogy, and in the case of force current analogy, it is nothing but a current. Understood? It's nothing but the current element. So in the case of velocity, so in the mechanical system, mechanical translational system, in the case of velocity, its corresponding element in the case of force voltage analogy is current I, and the force current analogy is voltage. That's true. Similarly, for mass element, you need to replace the mass element with the inductance L, and in the case of force current analogy, it should be replaced with the capacitance C, right? Similarly, the viscous friction coefficient B, that is replaced with the resistance R in the case of force voltage analogy, and the corresponding element in the case of force current analogy is conductance 1 by R. Similarly, the displacement, for displacement X, so displacement in translational system is represented as X. So this can be replaced with its corresponding equivalent quantity charge in the case of force voltage analogy, but in the case of force current analogy, it is nothing but a flux. Understood? So the stiffness constant K, it is nothing but in the case of force voltage analogy, it is represented with the reciprocal of capacitance, that is 1 by C, right? 1 by C, the reciprocal of capacitance. And in the case of force current analogy, it is nothing but 1 by L, the reciprocal of inductance. You need to remember these things to convert a mechanical translational system to its equivalent force current analogy or force voltage analogous system. Understood? So please do remember these things. So if you want, I will repeat it once again. The force is represented as voltage in the case of force voltage analogy. In force current, it is current, right? Velocity, the corresponding element in FV is current I. In the case of force current analogy, it is voltage, right? Mass is replaced with the inductance L, and force current analogy, it is in the capacitance. It is replaced with the capacitance. Similarly, for B, it is R. Here it is 1 by R. So for displacement, it is Q. Then it is flux. Okay. Now you see, just you just take an example, right? So I will explain this analogous system with an example, right? So for ease of remembrance, So I will tell you what are the things you need to do while finding the its analogous equivalence, right? So in the case of force voltage analogous, the independent variable force, the independent variable is force. Okay, so the force is replaced with, sorry. Okay, the force, its corresponding quantity is force should be replaced with the voltage E, voltage E, or it can be represented as P. Force E, or this is for force voltage analogy. This is for force voltage analogy, FV. So you can write it as FV. So similarly for velocity V, it can be replaced with the current I. The velocity V should be replaced with the current I. Similarly, for displacement x, the corresponding quantity is charge q in the case of force voltage analogy. Understood? Similarly, for the frictional coefficient of dashpot B, right? Frictional coefficient of dashpot B. So it should be R in the case of force voltage analogy. Similarly, for mass element M, it is the corresponding element is L. Understood? Similarly, for stiffness coefficient K, the corresponding element is 1 by C. Right? So these are all the things you need to remember in the case of force voltage analogy, right? In the case of force current analogy, you just see the variable force F should be replaced with the current I. You just see the differences. So here it is E or V, here it is I. Understood? So for velocity element, it should be voltage element, right? Voltage, velocity, it should be voltage, right? For displacement X, it is flux. Here in the case, in this force current analogy, it is flux phi. Understood? So for frictional coefficient or dashpot element B, it should be replaced with a 1 by R. It should be replaced with a 1 by R. For stiffness constant K should be replaced with the, you can use 1 by L for stiffness constant K. So if you remember these things, easily you can find the corresponding or analogous electrical system in the case of force current and force voltage analogy. Okay. You just see, so I will explain these things with an example, right? You just consider a small system, right? Just consider a small system. So I will show it in here. So this is a translational mechanical system. So I'm drawing this translational mechanical system. So these are all the reference points. Okay, these are all the reference points. So here you are having a spring element, right? Here you are having a spring element, and this spring is connected to another element or a mass element. It is connected to a mass element. and the force applied to it is represented as F of t, right? This is what the mechanical translational system. So you need to find its corresponding the force current as well as force voltage analogous system, right? So a spring constant here, stiffness, spring constant is K. For mass element, the displacement is represented as X. Okay, so now the applied force is F of t. So between this ground plane and mass element, there exists a frictional element, right? There exists a friction. It is represented as B. So this is what the mechanical system given. So first of all, you need to write the differential equation of this mechanical system. Okay, so let us write the differential equation of this mechanical system. How do you write the differential equation of this mechanical system? First of all, you need to draw the free body diagram, right? So let us draw the free body diagram. It will be easy to write the differential equation once you draw the free body diagram. So just to see here, only one mass element is there, right? So I'm drawing this free body diagram. Only one mass element is there. It is M. It is represented as M, and this force, applied force is F of t. Applied force is F of t here, and the opposing forces are the force due to this mass element. It is represented as Fm, and the other one force is Fk, right? Another one force is Fk due to the spring element. Another one opposing force is this Fb. Understood? Fb. Now we can write the applied force using Newton's second law. We can write the applied force F is equal to the opposing force, that is Fm. F is equal to Fm plus Fb plus Fk. So this we have discussed in the previous class, right? F equal to Fm plus Fp plus Fk. So now what is the equation for this Fm, for mass element? So for mass element, we can write Fm is equal to m into, here the displacement is x. So we can write it as m into dx square divided by dt square. M into dx square by dt square. Plus for the frictional element, dashpot element, it is b into dx divided by dt for the frictional element. Plus for the spring element, it is k into x. So now you have written this differential equation for this mechanical translational system. Understood? So now we need to convert this into its corresponding analogous system, that is force voltage analogy as well as force current analogy, right? So now let us see how we are obtaining this force voltage analogy. So for force voltage analogy, what you need to do, you need to replace the mass element, the frictional element or the dashpot element, as well as the spring element with its corresponding elements in the electrical system. So what is the corresponding element for this mass element in the case of force voltage analogy? So it should be replaced with the inductor L, right? Similarly for B can be replaced with the resistance R, and for K is to be replaced with the 1 by C, or the capacitance, the inverse of the capacitance. Similarly, the velocity element is replaced with the current I. What is velocity? dx divided by dt represents velocity, right? Displacement is x. Once you differentiate it, you will get velocity. If you differentiate it 2 times, you will get acceleration, right? So here m into dx square divided by dt square is there, right? So here you are having d by dt of dx by dt. So this dx by dt represents what? The velocity. Understood? So velocity should be replaced with the I, and this force should be replaced with the E of t or the voltage, right? So V of t or E of t, whatever the term you can use. Understood? So now just to say for this equation number 1, you can write its corresponding force voltage analogous equivalent. So what is that? E of t. For F, you will be putting E of t, isn't it? E of t is equal to, for M, you need to put L, right? So L into dx square by dt square is there, right? So dx square by dt square is there. So Here velocity should be replaced with a I. So dx square by dt square can be written as di divided by dt. Is it not? Di divided by dt plus r into I of t, or we can write r into I. So instead of I of t, you can write I also, right? So r into I plus, for the next element, see here b, this is velocity element. Dx by dt represents velocity. So here dx square by dt square is there. That is why we have written it as di by dt, right? Plus r into I of t, okay? R into I of t, or r into I, plus next for k into k, instead of k you need to put 1 by c, isn't it? For k you need to put 1 by c, right? So 1 by c into integral I of t, 1 by c into integral I of t into dt. Understood? For x, how will you write x? X is nothing but a displacement, right? So once you integrate it, you will get the velocity. Understood? So 1 by c into integral I of t into dt, right? Therefore, this is what the equation that represents its corresponding force voltage analogous system, right? So see here, one inductance is there, one resistance is there, similarly one capacitance is there, and these three elements are connected in cascade, isn't it? These three elements are connected in series. All these three elements are connected in series, right? Now we can draw its corresponding force voltage analogous system, right? So the applied voltage is E of t. So the applied voltage is E of t. Understood? So this is the applied voltage or the input voltage. Okay. So now you are having three elements. The first element is your inductance elements, right? Inductance elements. The next element is your capacitance. One capacitance is there, and another one resistance is also there, right? So these three elements are connected in series. Okay. So this is nothing but your L, this is nothing but your C, and this is nothing but your R. So you no need to write 1 by C here, right? So you can simply write a C. So LCR, right? So this is nothing but a symbol RLC series circuit, and the current flowing through the circuit should be represented as I of t. Current flowing through the circuit is I of t. Understood? So this is what your force voltage analogy. Force voltage analogy. Understood? So now let us see how to find its corresponding force current analogy, right? See. So for force current analogy, so let us see how to find its force current analogous system. So for force current analogous system, force current. So you need to replace this mass element with the capacitor. Okay, mass element with the C. Okay, B with the 1 by R. B with the 1 by R, and this K with the 1 by L. Okay, K with the 1 by L. Okay, now we see similarly the force F with similarly the force F, you can write I of t, right? Force current analogy. So there in force voltage analogy it was V of t. So for force current analogy it is I of t. Understood? So now you can write the, and so for this displacement x is nothing but your integral V of t, integral V of t. So now we can write the equation. The equation corresponding to the equation number 1. That is, for f can be replaced with a I of t, right? So we can write the equation as I of t is equal to, so instead of m, you can write C into d voltage dV divided by dt, isn't it? dV divided by dt, right? Plus 1 by r into, plus 1 by r into b, right? 1 by r into b, because b should be replaced with 1 by r. So this dx by dt is nothing but your v, right? dx by dt is now here v. So in that case, in the case of force voltage analogy, it was I, right? So here it is v, voltage. So 1 by r into v plus for the next element k, it is nothing but 1 by L. 1 by L into integral v of t, integral v of t into dt. 1 by L into integral v of t into dt. Understood? So see here, in the case of force voltage analogy, all these elements are connected in series. But in the case of force current analogy, you are replacing the voltage source with a current source. You are replacing the voltage source with a current source. Understood? So while replacing a voltage source to, or while converting a voltage source to current source, you need to connect all the elements in parallel. Understood? So here also you need to connect all the elements in parallel, because we are converting the voltage source into a current source, and therefore you need to convert or change all the voltage source into current source by connecting all the elements in parallel with the source. Okay, so let us see how I am making this circuit, right? So the current is I of t here, the current is I of t, this is what your current source. Okay, now the first component is your capacitance. Okay, so the capacitance, so now you have connected the capacitance here, which is in parallel with this current source. The next element is your inductance. Okay, the inductance L, this is the capacitance C, and the final element is your resistance. So you please, while drawing this diagram, you please draw it neatly, not like this, right? So this is your resistance. So this is what the diagram of, or the force current analogous circuit, force current analogous circuit. So I hope that I have got some idea about it, right? Thank you.